Log on, tune in, find out. Another good idea from Cambridge.
And I just realized that when I start talking about this, everybody thinks that because of the word tomography, this is going to be related to computer tomography, which is what you might have come across in the hospital. But this is not at all related. I mean, it's related on the theory side, but not really. This is nothing medical, really. So the problem that I'm addressing here is estimating the quantum state of a particular physical system. Many of you might have heard about recent developments in quantum computing. Quantum computers, simply put, are exploiting some physical phenomena to speed up computation, and basically you can do certain computations much faster on these computers than you would do otherwise in a classical computing system. But interestingly, the result of a quantum computation is basically a physical system which has a quantum state, and the answer to your question is encoded in the quantum state of that system, and that's not something that you can directly observe. You cannot open up your system and get that result out of it. So after your quantum computer produced you that result, you can play with that physical system that's the product of quantum computation. You can interact with it, you can make measurements on it, and then you can guess what the result was based on those measurements. But essentially, just trying to figure out what the response or what the answer was to your question is another statistical estimation problem, and this is called quantum state tomography. So the goal, we want to estimate the state of a system, and the tools that we can use are repeated physical measurements. And in quantum systems, it's a very interesting phenomenon that even if you know the state of the system and you know your measurement equipment perfectly, the outcome of your measurement is inherently stochastic. So it's very bad news, because that means that you cannot really get deterministic answers about that quantity of interest, but it's very good news for statisticians, because it means that this problem is a classical statistical estimation problem. It's also a very interesting one. And it's a very, very hard estimation problem as well. Just consider the following problem. If you don't know anything about the system, then what the parameter might be, then you're basically estimating in the order of 4 to the m real numbers, 4 to the m real degrees of freedom in case of an m-qubit system, and each of the single measurements provides you at most m bits of information per measurement. So you can imagine that you have to do a lot of these experiments, often in the order of like millions, to get any information about the parameter that you're trying to estimate. So we have to tackle this somehow, and one of the ways people try to tackle this is to introduce some sort of prior information that you might know about your parameter. For example, sparsity type of ideas that are also used in regression, or low rank assumptions. This is not what I'm interested in. I mean, I'm interested in it, but this is not what I'm going to talk about now. The particular subproblem that I worked on is designing adaptive experiments. The problem here is that there's a huge space in which you want to make measurements, or in which you want to make estimation, but there is also a huge number of possible measurements that you can make. And the vast majority of those measurements will not give you any information about the latent parameter at all. So the problem of experimental design is something which is very, very relevant in this particular statistical estimation problem. A bit more into the detail. I'm not going to tell you any details about the algorithms or anything that I'm using. The parameter that we are trying to estimate is conventionally called rho. It's a d by d complex density matrix, meaning that it has unit trace, and it's also positive definite. And in the case of m-qubit registers, this is going to be, d is going to be 2 to the m. So this d is the dimensionality of the quantum system. This is big, and this is why quantum computers are efficient, by the way. The measurements can be mathematically described as sets of positive operators m1 through md. You can, for a d-dimensional system, in the easiest scenario, you can have d possible discrete outcomes of each measurement. And for each of those outcomes, there is an associated positive operator m. And they are subject to the constraint that they have to sum up to identity. And the likelihood, so the probability of observing certain outcomes, is given by Born's rule. So the probability of observing the ith outcome is the trace of the product of the parameter that we are trying to estimate, this density matrix, and the operator corresponding to the ith outcome. And this condition ensures that these probabilities add up to 1. So this is the mathematical context. You can think of rho as basically parametrizing this discrete distribution, and then you're trying to do some sort of parameter fitting or model search in this space. Inference is, I think I should say, the most popular way of inference, so estimating rho from experimental data, is the maximum likelihood method. But it also has certain pathologies which are very, very bad from a physicist's point of view. So more and more physicists are basically shifting towards Bayesian methods. So maximum likelihood, the pathologies with maximum likelihood estimation are so bad that even physicists started to do Bayesian inference here. I also do Bayesian inference here. And the problem of adaptive sampling is given. So imagine that you're doing some measurements, and after the 100,000th measurement, you observed some partial data, and you now have to reconfigure your measurement equipment and tell the system a new set of these operators to use to do the next measurement. And the objective that I'm using in this work is the mutual information between the outcome of the next experiment and the latent parameter rho. This is also equivalent to maximizing the expected reduction in the posterior entropy. And this is there is nothing new about this. This is used in a lot of Bayesian experimental design studies. And on to my last slide, which is about results. I should say that these are probably the strongest results I've ever seen in my work, and I'll probably ever produce. These are for 2-qubit states. This is the number of measurements. You can see that these go up to 100,000 even for a 2-qubit system, which is basically useless from a computational point of view. And this is infidelity, which is roughly how bad we are, so lower values are better. And these are the two standard approaches. One is using separable measurements, which means that in a 2-qubit system, each of the qubits is encoded in, for example, each one with a photon, and separable measurements measure each of these 2 photons separately using some sort of physical instrument. The other one, MUB, or mutually unbiased basis, makes a joint measurement over the whole system. And this is, it's simple to understand that the separable thing uses much cheaper implementation, because you don't have to do anything like interference and things like that. So typically, if you want to implement these are going to be much cheaper to implement, and these are going to be very costly to implement in terms of implementation time and even like material cost. But the reason people are doing this MUB more expensive is because they are statistically more efficient. So you can see that there is a tiny little gap between them, but this is a log-log scale, so this actually amounts to a considerable savings in experimentation time. But these basically use a fixed set of measurements and randomly selecting amongst them, so no adaptivity. What if we throw in adaptivity? So I actually use my algorithm now to select amongst these fixed set of bases. And as you can see that both of these new curves basically line up on the red one. So if you actually allow for adaptive selection of measurements, it doesn't really matter whether you use the cheap implementation or the cheap physical instrument, or you use the more expensive mutually unbiased experiment, you basically get the same statistical efficiency. And that's a very important result practically, I think. But of course, now you have to think about implementing the adaptive selection with a classical computer in the background or something like that. And now we can go even further and allow for a more flexible set of still separable measurements. So implementing these is still very, very cheap compared to these MUBs, but now you're just allowed a bit more flexibility, and you combine it with this adaptive selection, and you get this black curve. And note that this difference here is actually huge because of the log scale. So you can achieve the same level of performance with like 10,000 measurements as the other ones achieve with 100,000 measurements. So this is a tenfold improvement over existing methods. And the important point is that this is only an illustration. This is just a 2-qubit system, and we have reasons to expect that if you go for higher level systems like 4 or 5 qubits, which are actually nowadays state of the art, then you can get like even larger improvements with this. So I have 1 minute left, which I think I will leave to the audience to ask questions if there are any. Thank you.
Yeah.
Speaking with considerable ignorance of quantum computing, you are performing thousands of measurements on a system in some quantum state. What are the issues which might arise if the system you're trying to observe change state when it is observed?
Yes, that's a very good question, actually. So I repeat the question. The question was, what when you're making several thousand measurements, what happens if the system changes during this process? Well, we know that if you make only a single measurement, the system will change, and you basically, when you measure a system, a quantum system, you destroy the quantum state. And therefore, how physicists got around this problem is to basically start from scratch. So you run your quantum computer, which is basically instant. So the time, the quantum computation time is basically building the computer. Once you've built a computer, it's basically instantly producing the results. So you produce a copy of your system, you measure it, and then you go back from square A0, you produce another copy and you measure it again. So basically, these are 100,000 different copies of the same system.
So you, in effect, you recreate the system each
yes,
time.
so these are essentially different photons, different physical systems that we are measuring.
There is some assurance about how likely it is that when you recreate it is in the identical state.
Yes, and that's actually encoded in this rho parameter. So the rho parameter accounts for uncertainty in creation of that quantum system.
Thank you.
So that's already in this formalism.
Okay, let's thank Ferenc again.